Welcome to the Explainer. Today, we are going to crack open this tiny digital fortress that lives inside pretty much all your devices. You know, the one that keeps your secrets safe. We're talking about ARM TrustZone.
All right, so let's start with a puzzle. It's a puzzle every single one of your devices has to solve. Think about it. How can your phone be this wide-open playground, running your banking app, your social media, some silly game you downloaded, and at the exact same time, be a super secure vault for your most private stuff, right? That's the big challenge, balancing all that openness with ironclad security. Well, the answer isn't something you can just download from an app store like an antivirus. Nope, it's way deeper than that. It's a feature that's literally built right into the silicon, into the core of the processor. And that is ARM TrustZone. It's what creates the separation at the most fundamental level possible. Okay, so let's really get into it. The easiest way to wrap your head around TrustZone: just imagine your device's processor is a kingdom, a sprawling kingdom. And right in the middle of it, there's this super fortified, you-can't-get-in fortress. So what TrustZone does is it splits the processor's entire operation into two completely separate worlds. They're hardware isolated, which is key. So on one side, you've got the non-secure world. Think of this as the bustling open kingdom. It's where your operating system lives, your web browser, all your apps. Then on the other side, you have the secure world. That's the inner fortress, and only the most trusted code is ever allowed to run there. This is the place that protects your fingerprint data when you unlock your phone or your credit card info when you tap to pay. All the really important stuff.
Okay, so how does the processor actually know which world it's in at any given split second? Well, this quote really nails it. It's all about location, location, location. I mean, think about it. It's like a real castle, right? The rules are different if you're standing in the king's private chambers versus out in the public marketplace. It's the same idea here. The processor's security state is literally determined by the memory address of the code it's executing. It's not a switch someone flips, it's just a fundamental property of where that code is.
All right, so if location is everything, that begs the question, right? Who draws the map? How does the system know where the fortress walls are supposed to be and where the open kingdom starts? Well, that whole process has a name: security attribution. What the system does is it basically takes a can of digital paint and labels every single part of its memory map. Each label is a security attribute, and that label tells the hardware exactly what that piece of memory is for. Is it inside the fortress? Is it out in the open kingdom? Or is it something else? And there are basically three of these labels you need to know. First, you've got S for secure. That's pretty straightforward. It's everything inside the fortress. Then you've got NS for non-secure. That's the open kingdom, where most stuff happens. But then there's this really clever third one, NSC, which stands for Non-Secure Callable. And you can just think of these as the heavily guarded gatehouses. They are the only approved ways to get into the fortress. So who's actually drawing these lines? Well, you've got two architects, basically. The first one is called the Security Attribution Unit, or SAU for short. This little guy lives inside the processor, and it lets the secure software itself draw and change these boundaries on the fly. It's like having a configurable blueprint for the fortress walls. And the second architect? That's the Implementation Defined Attribution Unit, or IDAU. Now, this one is different. Think of it as the original, unchangeable master blueprint that's literally burned into the chip by the manufacturer. It sets the default security layout, and it creates a baseline that software just can't mess with. Okay, so what happens if these two architects disagree? This is where it gets really smart. The rule is super simple. The most secure setting always wins, period. So just look at this table. If the fixed IDAU blueprint says a chunk of memory is secure, it doesn't matter what the software-based SAU tries to do, it stays secure. The system is designed to always default to the highest level of security. So the walls are up, the map is drawn, we're all set. But, you know, a fortress is pretty useless if you can't safely get messages or anything else in and out. So how does normal code running out in the non-secure world ask the secure world to do something for it? It's all about making sure that crossing is completely controlled. Yeah, you can't just have an ad from the non-secure world call a function inside the secure world. That would be like trying to just, jump over the castle wall. It's not going to happen. Instead, you have to go through a very specific pre-approved doorway, and that doorway is called a secure gateway veneer.
And this process is super controlled. Check it out. First, your non-secure code needs to call for help. But remember, it can't just shout over the wall. The call gets sent to one of those special NSC gatehouse areas we talked about. And sitting in that gatehouse is a special instruction, SG, which stands for Secure Gateway. Executing that SG instruction, well, that's like saying the secret password. The processor instantly switches into the secure state, and only then can it actually go into the fortress and run the secure code. It's basically a perfect digital airlock.
But here's the thing. The main processor core, the CPU, it isn't the only powerful thing in this kingdom. A modern chip has all sorts of other components that can access memory. A secure fortress doesn't do you much good if someone can just dig a tunnel underneath the walls, right? So TrustZone has to secure the entire system, not just the CPU.
So if the CPU is the king, you can think of these other components as powerful nobles. In tech terms, we call them bus masters. And these things, like a DMA controller, for example, can move data around all by themselves without even asking the king for permission. And you can see the problem there, right? If you don't keep them in check, a rogue noble from the non-secure side could just waltz in and read the king's private letters, totally bypassing the CPU's security.
To stop that from happening, chip designers put extra security gates all over the system. They're like checkpoints on all the digital highways, and they check every single data transfer to make sure it's playing by the rules. So, for instance, a designer can set up a gate that says your phone's fingerprint sensor can only be talked to by the secure world. It basically builds a permanent wall right around that piece of hardware.
And this brings us to a really important point. Not all these fortresses are built the same. TrustZone's architecture is actually pretty flexible. The design is going to be very different if it's protecting, say, a tiny little sensor in an IoT device versus the massive processor inside your smartphone.
Now, pretty much everything we've been talking about up to now, with the SAU, the IDAU, that SG instruction, that's all part of what's called TrustZone for microcontrollers, or the M profile. It's built to be super efficient. But the big, beefy A-profile processors inside your phone, they use a totally different model. Instead of having lots of little gates, they have one massive, highly fortified main gate. And that gate is controlled by an ultimate authority called the Secure Monitor.
And getting through that one main gate, it is governed by an incredibly strict set of rules. This document here, the SMC Calling Convention, is basically the official rulebook. It lays out exactly how the normal, non-secure operating system is allowed to even knock on that main gate to ask for help from the secure world. The magic word to get through this main gate is the SMC instruction. That stands for Secure Monitor Call. And when this instruction runs, it's not just a simple state switch. Oh no, it triggers a special kind of processor event, an exception, that completely stops normal execution and hands total control over to the secure monitor. And that is the most powerful, most privileged piece of software running on the entire chip. It is the ultimate security checkpoint.
So what's the big takeaway here? ARM TrustZone, it's not just some feature, it's a fundamental design choice, right from the ground up. By building this fortress directly into the hardware, it solves that big paradox we started with. It lets our devices be these open, creative playgrounds and be super secure vaults for our data at the same time. And as we've seen, the fortress design adapts, from the simple walls around a tiny sensor all the way to the grand citadel in your phone, which of course leaves us with one last question to chew on. As our world gets more and more connected, how will these digital fortresses need to change to protect us in the future?